Hello everyone, welcome back. So in the last lecture we talked about basically the relation between the quadrature operators and the ladder and the raising and the lowering operators, and we related both of them. And in the end we actually solved this problem wherein we tried to evaluate what is the uncertainty relation for the quadratures x1 and x2. But there were some questions, and I thought that the answer I think should be more precise, because this is only telling you that delta x1 into delta x2 is greater than 1/4. It's not telling the exact number. So I thought that we will try to take some time in this lecture and evaluate the uncertainty relations for various states. Alright, so that will be the agenda. And then in the process I'll also introduce what is known as a coherent state. And then in the end we will just try to talk about the interpretation of G2 function, and then we will stop there. Okay, that is the agenda for now for this lecture. Okay, so to start with, we have seen a vacuum state, right? And we have said that a vacuum state has this uncertainty relation. Basically delta x1 is half, delta x2 is half. So overall it should be 1/4, right? The area of the circle should be 1/4 in the dimensionless units. But how do we get this? We didn't give any justification. We said that this is what it is, like Heisenberg uncertainty principle. But then it turns out that you can actually prove it. Okay, how much this is. And the way we do that is by computing, let's say, the variance. Okay, let me say my variance in x1, delta x1 whole square. I can, from basic probability or random process theory, I can talk of this as basically expectation of x1 square minus expectation of x1 whole square. So this is what I was referring to when we were discussing the last question in the last lecture, right? How do we calculate exactly? This is what we were referring to. So how do we compute it? Okay, this is what we want to know. Once we compute it, we know, we can actually evaluate the uncertainty. Okay, so for that, we already know what is x1. Let's try to recap. If you have an x1 operator, that is going to be equal to half a plus a dagger. This is what we got, right? And then similarly, x2 operator was minus I by 2 a minus a dagger. So these are the operator definitions. So so basically to calculate the uncertainty or the variance, you need two quantities: the average of the expectation value of x1, expectation value of x1 square. If you know both, we can calculate. Okay. So how do we get the expectation value of x1? So what is essentially x1 for a vacuum state? How do we compute? We have the toolbox already. Okay, the way we calculate that is by calculating so x1, we know how to compute the expectation value, right? So for a ground state, I can write this as 0 x1 0. So this gives me the expectation value for a ground state. Remember this bracket notation, this is the initial and final states. We basically said in the integral form it has to be psi f operator times psi, right? That's similar thing here in the bracket notation. So what is this equal to? So this will be half 0 a plus a dagger. Okay, so now this I can write it as separate terms. Let's say half 0 a plus 0 a dagger. Now how much is my this brackets? If I have a dagger operating on 0, it's a raising operator, the creation operator. So it actually creates one photon. So you get to the number state 1, and number state 1 is orthogonal to 0. So the whole thing will go out to be 0, correct? Similarly, a is a lowering operator or the annihilation operator. So it basically gives you, if it operates on state 0, you essentially get 0. So this also goes to 0. So the entire thing is 0. Expectation of value of x1 is 0. Okay. And similarly, what does it mean expectation value of x1 is 0? Essentially, this is, we saw that the quadrature x1 is related to electric field. So if you take an average electric field in a vacuum state in 0 is 0. That's what this means. Okay. But do you expect the square of the electric field to be 0 in a vacuum state? No. Right? That's why we will compute x1 square. Expectation value for a ground state x1 square is how much? Okay, this I can do by, this will be 1/4 and then expectation value of a plus a dagger into a plus a dagger. Correct? This is what I want to compute. So 1/4, 0, I'll keep it. This will be a plus a dagger plus a dagger a plus a dagger a dagger. Okay. So without writing the details, I will conclude. We now know, right? A dagger square acting on 0 will give me what? Rising state, so 1 and 2, second state, photon number state 2, and that is again, perpendicular to 0. So this goes to 0. Similarly, this goes to 0, and even this goes to 0, the third term here. The reason is A acting on 0 will give me 0. Okay. And then that A dagger acting on that will give me 1. 1 again is orthogonal to 0. So that goes to 0. So only term that remains is A dagger. So A dagger acting on 0 will give me 1 and A acting on 1 will give me 0. So that is the only term survives, and we know that that is equal to 1. So basically this whole thing is equal to 1/4. Correct? So now if I call this as, let's say, my equation number 1, using 1 delta x1 is equal to square root of let's say x1 square minus x1 whole square, right? So this is going to be square root of 1/4, that's going to be equal to half. Similarly, if you do the same analysis, you will find that delta x2 is going to be half. Okay. So we got the uncertainty in the vacuum state, and it turns out that it is equal to delta x1 into delta x2 is equal to 1/4. This is a relation that we have derived, or rather we assumed in the beginning. But this need not be assumed, somebody has computed. So, I could have easily done all these things and then given you the expressions, no? But we took a different approach wherein we say that we describe the phenomena first, we try to interpret it and then come back. Okay. So this is a vacuum state, and so now clearly the electric field square is not equal to 0, is 1/4, and that's why the whole uncertainty variance is basically square root of that, and this is what we get. Okay. Delta x1, delta x2 is equal to 1/4. All right. Now, this is for the vacuum state. Let's try to do it for the photon number state. Okay. So, photon number state we already defined phenomenologically. We said that there is this number phase uncertainty. If my number uncertainty becomes very small, then the phase is completely uncertain. So, I'll represent it by a circle like this. And by approximate argument, by saying that delta x1 can go from here to here, basically, we said, delta x1 is something of the order of, I said, twice the n plus half whole square, rather whole to the power of half. And then delta x2 is similar, and then finally we came up with some number, delta x2 is also in the similar order, n plus half. Yeah, okay. But this is not precise, because we are saying only approximately this much, okay. But now we have all the tools to actually compute it correctly. How do we do that? The same approach as before. We know that delta x1 whole square is equal to delta x1 average value of x1 square minus x1 whole square. Okay. But now I want to do it for a number state. And by the way, if you recall our basic understanding, we said that number states are not minimum uncertainty states, right? We'll just look at that. Okay. So now, what is my expectation value of x1 here for a number state? So this is going to be, so I'll take a bracket with the state n, x1 acting on n, right? So again, I have the same idea. Okay, this time let me try doing it for 2 instead of 1, x2. So this is going to be minus I by 2 n a minus a dagger n, correct? So now the same thing basically. This will again split into two parts. A dagger, okay, this will be minus I by 2 n acting this one plus n, oh this is not plus, it's minus n A dagger acting on n, right? So again, this orthogonality will tell me that this term is going to 0. Both terms are going to 0. So my expectation value is 0 for x2. Okay. This is somewhat surprising in some sense. The reason is, this is a photon number state, right? Vacuum state I can understand that the electric field is going to 0, right? Or in this case it's magnetic field, let's say, it's proportional to P, right? X2. But X1 also will turn out to be 0 anyway. So the electric field is going to 0. But let's say if you have a large number of photons in a state, let's say 10,000 photons, it's approaching a classical limit. Why should the expectation value of electric field go to 0? Why should quadrature of x1 go to 0? Okay. That's a contradiction, right? I mean, if you have a large number of photons, if you have a number state consisting of 10,000 photons, or 1 million photons, 10 million photons, whatever. If you have a large number of photons, it's effectively classical field. There should be electric field, the expectation value should be non-zero. But for number state, it is turning out to be 0. We'll reconcile that in a moment, okay? So, then this is the expectation value of x2. Then what is my x2 square? Same thing goes, x2 whole square. Can you also track time and tell me if I'm crossing 30 minutes? Okay. I'll try to think of, maybe I'll split it if required. Well, let's see if required. Okay. So x2 square is going to be again the same thing, I by 2. So basically minus, so I square, so minus half, or rather minus 1/4. And then I'll simply write out the terms now. Instead of a dagger, minus a dagger, minus a dagger a, minus plus. That's what I think it should be. A minus a dagger into a minus a dagger, minus plus a dagger 0, or rather n. Okay. So now which terms will survive? A will go first for sure. A dagger will go. So if we have A, so minus I can take out. A acting on n will give me n minus 1. Again acting on A dagger will act on it and bring it back. So this should survive. A dagger will give me n plus 1. Again this will, so both will survive, right? Two terms will survive here. Okay. So now, so this should be minus, if I take out 1/4 n acting on A dagger plus n acting on A dagger A. Or rather, I should not say n acting on, A dagger A acting on n. The operator acts on the number state, not the state acting on the operator. Sorry. Yeah. Okay. So now what is this number now? 1/4. A dagger acting on n will give me root of n plus 1. And then lowering operator will give me the same thing. So this is n plus 1 effectively, correct? Square root of n plus 1 into square root of n plus 1. And this other case, it should be n. So basically we have 2n plus 1 divided by 4. Similar, okay, now my delta x is going to be equal to how much? So if I jump steps, delta x2 is going to be equal to square root of 2n plus 1 divided by 2, and that is also equal to delta x1. Okay. So what is my uncertainty relation? Delta x1, delta x2 is equal to 1/4 2n plus 1. So if I take out 2, essentially you get half n plus half. Okay. So now this is interesting. The reason is, let's consider what happens when n equal to 0. Okay, delta x1 times delta x2 is equal to 1/4. N equal to 1. Delta x1, delta x2 should be equal to 3/2 into half, so 3/4. Okay. So basically, for any state, number state, ground state, n equal to 0 if you put, you're getting the minimum uncertainty, vacuum state, correct? And any state, any state with n greater than or equal to 1 does not have minimum uncertainty. Right? That's what we are saying. So, okay, the question is n equal to 0 number state is it a vacuum state? Yes, there are no photons in it, so it's vacuum state. X1 expectation is equal to 0, x2 expectation also is 0. So it's undefined. It's truly random. Okay. Essentially, it's vacuum state, x1 and x2 are 0. Centered around that, you have this x1 and x2, right? But now, number state, you don't have a minimum uncertainty state. As the number of photons increases, uncertainty increases. Why does it make sense? So both x1 and x2 both are same. So now what we are saying is, as a large number of photons you get, what happens? It's effectively increasing. As the number of photons increases, uncertainty is increasing. And it's effectively telling us that, think about what happens with, number phase uncertainty. What is delta n? If you fix the number, delta n reduces. So your delta phi should be very large. Overall, the product is large. Okay. Here, this is also telling us that, but phase uncertainty is there. That there is no number uncertainty, but phase uncertainty is there. So because of that, in terms of quadratures also, you get uncertainty. And it's not a fixed thing. As the number of photons increases, the uncertainty is also increasing. Okay? Okay. Now the question is, what was troubling us before, right? So we said, x1 expectation is going to be 0, x2 expectation is going to be 0. But how does it make sense that when I have a million or 1 billion photons, it has an expectation to be 0, right? Because we know that as we approach the classical limit, there's a certain electric field, there's a value of electric field, right? So this seems to be a contradiction. But it turns out that, so the way to get around that is by understanding that a photon number state cannot represent a classical electric field. Classical electric field is something different. Okay. And no single photon's number state can represent a classical electric field. You have to consider a superposition of photon number states. Okay. That is how we can represent a classical electric field. And so that is what we'll call as a coherent state, right? We define and we'll try to give an expression and try to understand what it means. So when we talked about the phenomenological description, we said that the coherent state is simply a minimum uncertainty state with a length which is basically given by alpha. Alpha is root of n plus half, and then there's a phi and so on, right? That's how we define this with this complex number. A represents a complex number. Alpha represents a complex number, and the magnitude and phase is what we have. So now what we'll do is, we can actually define the coherent state. This is a definition that we are giving, okay? Saying that it's a superposition. So I have my number states here. So all of them are in summation. So basically I'm considering a superposition of number states, and there is some coefficient associated with each state. When I do that, and there's some normalization factor. When I build a number state of this form, I can actually show that the uncertainty is minimum. We will show that, okay? But that you have to accept. There is a way to derive it. When you understand, when we talked about electric field, right? Let's say electric field means x1. When you took a quadrature of, let's say 0 state, right? With x1, we got expectation value of this is, 0 is this much, right? And then with, let's say 1 also we are getting this, right? and 2 also we will get this. So basically, let's say I'm taking these 3 number states and I'm getting my expectations to be 0. Now I'll say, no, I won't do this. I will construct a superposition in such a way that psi n is going to be equal to C1 times number state 0 plus C2 times number state 1 plus C3 times number state 3. C1, C2, C0, C1, C2 effectively. Well, you get the drift. Simply it should be, let's say, C0 times 0 state plus C1 times 1 plus C2 times 2 and so on. Okay. So what I'm effectively writing is, I'm constructing a state, and now instead of psi n, I'm calling it, let's say, alpha. So effectively my alpha is some coefficient times summation n equal to 0 to infinity Cn n. Okay. Starting with that, we can actually show that your this coherent state will come out to be this. Okay, we are not showing the derivation, we just give the final expression, that's it. All right, so it will turn out to be this, what is given here, expression. One of the important things I want you to realize is that this coherent state alpha, it is not an eigenfunction of the Hamiltonian. When will it be a Hamiltonian? So basically, if I take H in this case, Hamiltonian operator acting on alpha, it basically has what? A dagger. Sorry, A dagger A plus half, right? That's a Hamiltonian operator. So if you have that acting on this, you will quickly see that this will not be equal to some constant times alpha. It will not be equal. So we can easily show that because we know A dagger A plus half is, into H cross omega is my Hamiltonian. We can show this result. So basically, alpha is not a eigenfunction of H, but it turns out that alpha is an eigenfunction of A, annihilation operator. Okay, so this is 1 and this is 2 points to remember. Okay, of A operator, right? How does it work? Let's try to verify it. We have the tools to do that, right? So if I have A, operator A acting on alpha, what do we expect? What is operator A? It acts on a number state and produces a lower state, right? So I'll simply substitute the whole thing, okay? Okay, let me be a little lazy here. I'll simply call this as some C, I'll call this, okay? Equal to, let's say, C, let's say something, simply to simplify my life. So this is C summation n equal to 0 to infinity alpha power n divided by root of n factorial A acting on n, right? So the rest of the things are constants. So if I do that, we'll see this, that this is going to be C summation n equal to 0 to infinity alpha n divided by root of n minus, n factorial. A acting on n will give me n times n minus 1. Well, okay, so I should actually make my summation go from 1 to infinity because I can't talk of I can't talk of -1 as my state, okay? N is going from 1 to infinity. So then you'll quickly see that this is equal to, alpha times C times summation n equal to 1 to infinity alpha power n minus 1 divided by root of n minus 1, because n and n factorial, right? N and n factorial, so it will be only n minus 1 factorial, root of n minus 1 factorial, okay, into n minus 1. By putting n equal to n plus 1, I'll immediately see that this is nothing but the coherent state, right? C into, if I put n equal to n plus 1, and it's going to infinity, so it doesn't really matter whether I call it 0 or 1, whatever. It's just a change of variables. So this is equal to alpha times my alpha, Okay, the number alpha. Okay, what is that? We will try to understand. With me so far? So we essentially showed that this is eigenstate of annihilation operator. Why am I calling annihilation? Annihilation, I think yesterday I was not using that term. So, but essentially saying that lowering operator. We are reducing, so you're annihilating one photon or creating one photon. That's the alternative name for this. Alright. So this is so far this one. Now, so what? Okay. One way to consider what this implies is basically, let's put it back here. We know that your A acting on alpha is going to give me alpha times alpha. If I take a conjugate, I can write it as alpha times A star, or A dagger rather, is going to be equal to alpha times alpha star. Alpha is a complex number. If I don't put the operator sign, it is a complex number. It's not a ket. In this case, in the first case it's a bra. Sorry, this is a ket and this is a bra, right? So now, if I combine both of them in a product, effectively I'll end up with alpha A dagger A alpha is going to be equal to alpha alpha star, right? That's what I think it should be. So effectively that's equal to alpha square. Okay, and this is my number operator. Number operator acting on a state will give me number of photons in the state, and I'll call the number of photons as okay, gives number of photons. So n bar is equal to alpha square. So basically my alpha square, it's a complex number, right? So modulus of it is basically alpha into alpha star conjugate, right? So my number of photons is effectively going to be square root of the length of the, so alpha is my length of the vector, right? The phasor rather, not vector, phasor. And the length of it is basically average number, square root of average number of photons. Okay? Okay? Similarly, I can even show that if I go through the math, I'm not doing it, delta n is also going to be equal to square root of n bar. So essentially what we are saying is this sort of a state that we constructed as a superposition of all these number states has Poissonian statistics. Its variance is equal to the mean. Okay, so it has Poissonian statistics. Okay, so that's what we showed. All right. Any questions? Okay, good. So, yeah. Sorry? 30 minutes. Okay. Yeah, I mean, well, let me quickly do the uncertainty and then I'll finish off. Okay. I think it will come to 40-ish. Okay, let's see. All right. Okay. So, yeah, this is my coherent state. Okay. Now we understand why we need to define a coherent state. Okay. Now, let's try to calculate, the uncertainty of the coherent state, because now we have defined this as this one, right? But what is the uncertainty region for a coherent state? We have given it as minimum uncertainty state, 1/4, but we didn't prove it. Okay, let's actually try to calculate it once. And so again, the same concept that we kept on applying, right? So how do we calculate the uncertainty? So delta x1 square, delta x1 variance is equal to delta x1 square minus expectation value of x1 whole square. Okay, now we did for number state, we did for ground state. Now we want to do it for coherent state. So the first thing I'll start with is my expectation value of x1. For both the cases in the past, it was equal to 0. Now what will be the expectation value of x1 for a coherent state? Okay, so this is going to be half. Well, let me expand it and write it. So basically x1 is a plus a dagger. So right, plus alpha A dagger. Okay. Now we saw already what A does on alpha. It creates alpha, correct? Right? Now what does A dagger do on alpha? It creates conjugate alpha star. Okay. So now effectively this is going to be equal to half alpha plus alpha star. Correct? Because conjugate, A dagger operating on alpha will give me conjugate of alpha. Okay. Because remember, our definition was that alpha equal to, let's say, mod of alpha e power I phi. Correct? So alpha star is going to be alpha, same length, but minus I phi, conjugate essentially. Okay. So now, if I were to use that into my expression here, so this is going to be equal to half mod of alpha exponential I phi plus exponential minus I phi. So clearly this is equal to alpha times cos phi. Okay. So this is not zero, but projection on the x1 axis. Okay. If I look at this, my x1 quadrature essentially is going to be, the average value of x1 quadrature is going to be this, which is simply cos phi, alpha times cos phi. Okay. No surprises. Similarly, you should work it out, but alpha times x2 on alpha will give me alpha times sin phi. It's projection on the y-axis. Okay. So that is good. At least it's not zero, and it's give me some cosine. X1 quadrature had the cosine term. Okay. So that's how you get to the, again, this is related, and that's why coherent states are interesting. Okay. And now what happens to my uncertainty, right? So for that I need to calculate alpha acting on x1 square. How do I do that? X1 square is going to be 1/4 alpha AA plus A dagger plus A dagger A plus A dagger alpha. Correct? A dagger acting twice will not be orthogonal, so this will go to 0. This will go to 0. So what about A dagger A and A dagger? Okay. I know A dagger A is my number state, but A dagger, we know the commutation between, commutator bracket A dagger is going to be equal to 1. So A dagger is going to be equal to 1 plus A dagger A. So I'll put that in here. So I'll say this is 1/4 expectation alpha 1 plus 2A dagger A alpha. That's going to be equal to what? Oh, sorry. A dagger acting on alpha will give me what? No, that's a mistake. A dagger acting on this cannot be equal to 0. I was hasty. Okay, sorry. It's alpha square. Alpha acting on alpha will give me alpha again, right? And second time it acts, A square means alpha square. So A acting twice on alpha will give me anyway, alpha, inner product of alpha with itself is 1 anyway. So this will be alpha square. A dagger I said is 1 plus A dagger A, and A dagger A will give me the number of photons. So I'll write it as rather plus 1 plus 2 into, when A dagger acts I get an alpha, and then A acts I get an alpha sorry, A dagger acts, you get a alpha star. A acts, you get an alpha plus A dagger. So A star, sorry, A conjugate twice square. That is my product. Okay, this is what you end up getting. Okay, so this is equal to this. If I combine this if I combine, I get alpha plus alpha conjugate whole square. So this is going to be my alpha plus alpha conjugate whole square plus 1. The whole thing has a bracket 1 by 4. Okay. So now clearly my expectation value of delta x1 is going to be equal to square root of this guy 1/4. I'll take out 1/4. So okay, let's take it out easier. Square root of that will give me half, and then this is alpha plus alpha star whole square minus, or rather plus 1. Mean of this is what? Mean square. So that's going to be 1 by 4. So 1 by 4 will come out anyway. Alpha plus alpha star whole square. Right? So that's going to be equal to 1/2. Similarly, delta x2 is going to be equal to 1/2. So my uncertainty delta x1, delta x2 is equal to 1/4. So if I have a coherent state, I'll have my uncertainty relation to be minimum. All right. So, I mean, we can also define, this is one step. And now you can have a large number of photons as well in this. Because, you just essentially have the superposition of various number states. You put larger, but the only thing is the coefficient of the number states, larger states, for example, is n factorial. If you go to n large, the denominator increases, the amplitude reduces, the contribution reduces, but eventually, it will be summation of something. Okay. And all of them will go and add in such phase that you will end up getting a perfect monochromatic wave, which has a Poisson statistics and also has a minimum uncertainty. This is what a laser output would be. This is the quantum theory of explaining laser output. Even in the classical case, this will give you the same thing. Okay. I mean, you can go even one step forward. You can define what is a squeeze state. A squeeze state will be some other superposition. I mean, we'll have to look at, how the things are, but some other superposition. And then compute the uncertainties for that as well. It will be greater than, of course, minimum uncertainty. But in principle, you can construct it out of number states. So number states, basically, like you are talking of 1, 2, 3 photons. Those are number states. You combine all of that, you get the coherent state. Let's say there are 10,000 photons. You can think of one photon state of some amplitude, 2 photon state of some amplitude, 3 photon state of some amplitude, and so on. Eventually, the number will come out to be 10,000 of different amplitudes. That will give you a classical electric field. Okay. So yeah, I mean, we'll not touch the squeeze part, but anyway, that's how it is. Okay. So I mean, it's somewhat beautiful, I believe. Yeah. Okay. That everything is getting tied up. So yeah. Who said a thing of beauty is joy forever? I don't know. Okay. All right. Anyway. Okay. All right. So basically, the last thing I just want to touch upon is that, we talked about the Hanbury-Brown-Twiss experiment, and we talked about G2 function that goes to 0, right? For suppose on light, anti-bunching. We talked about that. Now, I mean, we just, qualitatively said that it will be less than, just that there won't be coincidences. So basically, G2 will go to 0, as if you have single photon sources. So you can actually consider number states. And you can define electric field amplitudes that are coming into beam splitter and then combining, and then same interferometer experiment, all that we can consider it theoretically, and we can actually show that the G2 of 0 is equal to n into n minus 1 divided by n square. I'm not proving it. I'm just giving you that this is what it is going to be. Okay, can be shown. Okay. This can be shown, and I think Mark Fox has, this is again from Mark Fox, okay? He has a derivation of this also. So now, what is the implication of this? Okay, so let us try to write it. Let's try to tabulate n, and then let's say G2 of 0. If your number of photons is 0, there's nothing to, it's indeterminate anyway, there's nothing, vacuum state. If you have number of photons to be 1, my G2 is going to be what? 1 by 1. So, well, no, 0. G2 is going to be 0. Number of photons is 2. This is going to be equal to n minus 1. So, it's going to be half. Number of photons is 3. This is going to be 2 by 3. Number of photons is 4. It's going to be 3 by 4. And similarly 4 by 5. Okay. So, essentially, as n increases, G2 of 0 approaches 1. Okay. So now what we see is, if you measure G2 function, second order correlation function, it is a very good signature of single photon sources. Okay. So that's what we said anyway, but we are theoretically also showing that G2 of 0 is a good signature. I don't know what, good quote unquote of quantum light or single photons. Single photons. All right. So it's very, very common to actually see G2 everywhere in quantum optic experiments. All right. So this essentially ties up my discussion about the states and uncertainties and so on. So we have introduced all the basic concepts. You might wonder, why do we need this? Well, the idea is that, if you want to understand the current literature, you need to know the basic terminology. If you don't, you can't read the papers. Okay. So this sort of, I think, introduces you all the basic terminologies. You should be able to read papers and make some sense out of it right now. Okay. There are still, of course, more advanced things. But yeah. Okay. This is where it is. Right. This is one of the frontiers. Any questions? All right. If there are no questions, we'll stop here. So my last lecture for this course would be on applications. So we kept on developing the theory. First we gave a description, and then we developed the theory for it, and we tied all of that up. I'll try to show you a couple of examples. One example essentially to show you that how this can be useful. Okay, one application. Okay, and then I'll close it with where we left off. Okay. So we'll meet you in the next lecture. Thank you very much for your attention.